The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
This thing is great for sheet metal, but most of the time I only need tiny bends in tiny pieces and I don't want to set up this thing. Also, I don't want to act like a caveman doing things with my hands. I'm electronics enthusiast, so let's build an electronics metal bending machine that helps me with small tiny parts. Let's get started.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
Welcome back to Element 14 Presents. I'm Clem, and in this episode we're building a metal forming machine, a tiny electronic one. I don't want to crank levers and put stuff together with my bare hands like a caveman. I want it to be automatic. So the bending itself is a manual process, so that you can go to precise angles, but all the clamping and stuff, that should be done completely automatic, and the machine should know when it's correctly clamped. So no end stops, no setting some values, it should do it automatically. Let's look what we are going to need for this project. Every time I want to move something to a certain point, I use stepper motors, known for precise movement. So I want the machine to clamp in a piece of material that I can then bend, and it should know when it has to stop and how much force it needs to apply to accomplish that. So the way you usually put a stepper to a specific point is home it and then count how many steps you have to go to that specific point. The other version to know when it has reached a point is just using homing switches, meaning end stops, just mechanical switches, and if the carriage bumps into that, you know that it's at the point. I could do that with just these switches, but if the material thickness changes or the shape of the material, that homing point would change and I would have to readjust for everything, and that's exactly what I don't want. The machine should just adapt to whatever I put in and clamp it correctly with just a push of a button. No need for me to worry about any settings. That's the goal. There is a way to determine the home position without having to use any switches. There is a certain kind of Czech 3D printer that uses that to a great extent to determine the home position for all the axes. And they use the TMC 2130 stepper driver. This is one I have in hand. And this stepper driver allows you to use a feature called stall guard. So it knows when it has bumped into things by measuring the current that the motor consumes. So if that exceeds a certain threshold, the motor knows, or the stepper driver knows, that it has bumped into something and will stop or reverse the direction, whatever you like to program. We can also use that feature to calculate the load that is on the motor in that moment, and with that calculate the clamping force. So we can make an adaptive motor control loop that allows me to put in whatever material I want, have it clamped with the right force, and then with just a push of a button release it again. And another push of the button to clamp the next piece or the next bend position, and I don't have to set anything manually. It just does it automatically. Because I use these specialized TMC 2130 stepper drivers, I have to be pretty conscious about what microcontroller I use. Because there's a catch. These modules are mostly used in 3D printers, and those use mostly the range of the 80 mega 328 to 2560 microcontrollers. So there are a lot of libraries that depend on those specific microcontrollers, and they won't work with other ones. I really wanted to use the new Arduino Nano Every, but turns out those libraries are not compatible. Direct register manipulation allows me to have the motor step all the time, and the microcontroller waits for interrupts like new commands or the stall guard feature to trigger. So that's a lot smoother operation than just having a loop that steps the motor over and over and checks for incoming signals in between. That would lead to jitter. So let's start off this project with mechanical design. I'm using Fusion 360 as always to draw them up, print out some files with my 3D printer and put it together using some aluminum profiles, 40-20 and 20-20 extrusion in that case, with some angle brackets and some screws and nuts and bolts, and see if that moves on its own. I'm also using stainless steel threaded rod, M10 in this case, for the very specific reason that I got M10 couplers already in my workshop, so I'm trying to use up some older parts. I hope that the stainless steel threaded rod gives me a little bit more leeway in terms of rust and lubrication, so I can make this work reliably over a longer period of time. To use the stall guard feature on the TMC motor drivers, I need to have them in SPI mode, serial peripheral interface. So it's important that on the bottom of these chips there is a jumper that has to be open to have them in SPI mode. If you want to use them in standalone mode, just close that jumper and it will only listen to step direction and the config pins for the stepping. So if we have it in SPI mode, it needs to be configured via SPI. If you don't configure it in the code, the stepper motor won't react to any signals. I've wired up a basic circuit for my stepper drivers and my Arduino Nano on some perf board with just some wires, and turns out it doesn't work because I need to have the SPI wired up to the hardware SPI bus on the Arduino and not any pins that I would set in a software SPI mode. That just doesn't work. I think it's not up to the speed of the hardware SPI, and the TMC expects a certain speed. So great, that doesn't work, so I have to rebuild all the electronics and make it work a second time. And I want to control two motors, so I'm wiring up two SPI buses, or two modules to one SPI bus with different chip select lines. And I hope I can make them work in tandem. If that doesn't work, I need to use two motors with one driver. The TMC 2130 is able to handle those, so you can pump more than 2 amps through it. That's not a problem. And I won't get over, I think, 600 milliamps per motor. So if I set it to 1000 milliamps on one stepper driver module, that should be enough in theory, and won't burn out any chips in case I can't get the SPI to work. So the second SPI bus had a little bit of trouble. Strangely enough, the second one, the B channel, worked perfectly. The A channel has some kind of problem. So I think that's a timing issue between the SPI buses. So maybe I need some additional pull-ups. Maybe there's a voltage drop in the lines, so the signals are not correctly. I don't really know. And now that I have it moving, I have the next problem. It's just not enough clamping force. And I couldn't fix that in code. It's just the stepper motors exceed their maximum capabilities. So I need to have more force. And the way you do that is with a gearbox. And I need it to be compact to fit on my machine, so I don't have to redesign everything. So I got online, and on Thingiverse there is a design from 2011 on the early days of consumer 3D printers. There's a design linked below for a planetary gearbox for 3D printers. It says it's untested, it doesn't really work, or it's not a verified design, but I give it a go anyway. Turns out modern 3D printers can print that file, at least mine can, without any supports. So that's pretty interesting how far we have come. In previous days that was a design that needed a lot of supports. I've printed that on 2 printers, so I have 2 sets in different colors and can switch out the parts to see if both printers exactly print the same, so the parts should be compatible, and turns out they are. And I have to redesign the front plate to accommodate for the bearing size that I have in stock, which are just skate bearings. I use them all the time because they are the easiest to get and the cheapest, and they do the job, so why should I use anything else? Make some adjustments in the design and print that out and assemble it. And now I have a planetary gearbox with a ratio of 1:5 or 5:1, so I need 5 turns of the motor to have 1 turn of the output, and that should multiply the power of clamping force by 5, and I hope that's enough. With a lot of lubrication, these gearbox designs actually work really good, so I can say now they are verified. You just have to use an additional mounting plate that holds the bearing that you want to use. You can download all these files at our video page on element14.com, and I've also linked the original design there. So you can try out to make your own planetary gearbox, which is also a great test for the accuracy of your 3D printer. So that should go together without any hassle, if your printer prints perfectly to size.
Want to build the project in this episode? Want to download the code? Find the parts list? Want to ask a specific question and know this host will answer it? Simply take out your phone and point your camera at this QR code. This will take you right to all the details you need to get started. We'll see you on the Element 14 community.
Now that the mechanical thing is finally done, let's look at the code. And it's a mess. This is the code for my metal forming machine. It's based on some examples from the TMC stepper library, so you may recognize some of these portions. I put them directly because I don't understand them perfectly, but they finally work. And I have left in some portions of the code so you can experiment with that and build upon it. So first we have to include the TMC stepper library, obviously. We have to include all the pins or define all the pins. Keep in mind that all these serial communication pins, the SPI pins, have to be the hardware pins, not just any pins that's suggested by software MOSI and software MISO and 0 o'clock. You need to have the hardware pins. It doesn't work on any other pins on an Arduino Nano. And this is meant to be run on a 328P based Arduino board like an Uno or the classic Nano. I couldn't get it to work on any other microcontroller because the stepping is based on direct register manipulation, and that is hardware specific. Of course, we also need some inputs for my buttons. I use the analog pins, not because I want analog inputs. I just use them because they are on the opposite side of the board and that's easier to wire up. This is the RSense value. That's very important for current sensing. For the TMC 2130, it's 0.11F. If you have a different stepper motor driver, you need to have a different value. You find that in the documentation. We do 2 instances of stepper driver, TMC 2130 stepper driver instances. We actually only use the second one. So channel B is the only one that's actually used, but I keep everything in there, just you can build upon, and maybe you can make it work with both at the same time. I had trouble with that, but I'm sure there's somebody out there in the Element 14 community that knows how to deal with them. This is needed for the actual stepping, so this function inverts the step pin, and that is much faster than I could do it with just digital write signals and waiting in between. In the setup loop, we begin SPI, we begin serial port for debugging and also for listening to commands. Declare the pin modes, and now this portion and also that portion is the configuration for each of the stepper drivers. We only need one as before. In my case, driver 2 is the active one. But keep in mind, if you use the stepper drivers in SPI mode, you have to configure them with SPI. If you want to use them standalone, you need to solder a jumper, and then SPI doesn't work anymore. But if that jumper is open, you need to have this configuration over SPI, regardless if you control it over SPI or if you control it over the step direction signals. Stall value is predetermined up here as 5. This is directly taken from the example that's also needed for the smooth and fast stepping. In the loop, we check for time. We need that later. We check if one of the buttons have been pressed. If so, we enable or disable the stepper driver. Stepping works continuously, so the step pin gets pulsed all the time, and we stop and engage the motor just by pulling the enable pin high or low. Low means it goes, and these both are mixed up because I have wired them differently on my board. So that's just a little bit mixed up, no matter what. While serial available, it means if the USB cable is connected, it also reads these buttons and acts accordingly, but it also listens to what's coming over the serial port. If there is a 0 coming or a 1, 0 means disable, 1 means enable the stepper motor. This is to illustrate how you would do that with a different motor driver, the TMC2660. Fun fact, that's the one that's on the Duet 3D printer board. That needs a different command, but the TMC2130 can just be enabled and disabled with the enable pin. If it reads a plus, we increase the speed. If it reads a minus, we decrease the speed. It's the other way around here because that is a value for delay and not for speed. So the more delay, the slower it gets. The stall value can be calibrated with these 3 buttons. 5 is the standard value. I determined that by trial and error, so it turns out 5 gave me the best results for my application, but that is dependent on your stepper motor driver and the motor itself, and also the gearing that you have on there. So your value can be different, but I suggest starting with 5 and going from there. And this has a calibration function, so if I think I need more or less of a value, 4 decreases the value, 6 increases it, and it gets constantly put out over the serial port, so I can read what is the current value and note that when I have found the perfect value for my application. And with the star button, you can change the direction of the motors. And this function gets pulled every 100 milliseconds, which checks if the motor has stalled. We do that by polling the status of the driver, waiting a little bit, and then we can say if the result that we get from the status polling is 0, that means the motor has stalled. If that is true, we invert the direction pin and let it move back. If the motor has not stalled, that value will be the RMS current value that the motor currently takes, and with that we could calculate the force that is currently applied. In my setup, the calculation is very difficult and would not be reliable because I have so much gearing on my stepper motors. There is a lot of slack in there. It's just not reliable. But if you have a direct drive system, meaning the motor directly presses on a belt or on like a threaded rod, then you could directly calculate the clamping force with that RMS current value. In my case, I'm only checking if it's 0, that means the motor has stalled, and then I'm inverting the direction to make it go back. That's basically the same thing with sensorless homing. So if the motor stalls, we go back a bit. If I would make it stop, that would be just a sensorless homing function. I want to go a little bit back to reach a stable point, and then I press the red button to keep it in place and do my bend. And of course it also puts out all this data over serial point, and the format is in that way that I can use the plot function of the Arduino IDE to see a graph of the forces that are applied and to see a visual indication when the motor has stalled. To finish the appearance of my machine, I use the same buttons that Caleb always recommends in his videos. These are these tiny push buttons. They are really great. They feel very satisfying. I use a red one and a green one, of course, for stop and go, and some laser cut acrylic. And I'm trying a new technique where I spray paint the acrylic, laser the contours, and then I laser the writing on there on the backside in a mirrored way, and then I give that backside another coating with a different color of paint. And if you turn it over, you have like an embedded writing in there that's completely flush on the outside, and you can also put lights behind it to make it shine through. I didn't implement it that good, it's my first try. So I scrubbed a little bit of paint away while assembling it with the cables. But exactly on that portion, the LEDs from the Arduino Nano shine through, so you can call that a feature if you want. I call it a feature. It's not a bug, it's a feature. Looks like we are ready to bend some metal. I have two applications that I want to show you. One is making a tiny hook for my workshop, so that's a few bends into a piece of brass, drilling a hole and screwing it to the wall. So that's one application that I need all the time when I need a hook that has a specific size or fits into something. I used a very tiny English wheel to give a compound curve to the aluminium skid plate for an RC car. So that is my tiny metal forming machine. If I would do this project again and had more time and budget for it, I would try to use Trinamics BLDC motor drivers. They support a lot beefier motors, so I could get more force, but they're also supporting stall guards, so they can sense the load that is applied. And that will enable me to maybe make a real metal forming press that has enough form to stamp metal and shear it and press it. That would be a substantial upgrade, but it might break the bank. Do you have any ideas for cheaper upgrades? Any mechanical solutions to get more force out of a tiny motors that I haven't covered in this episode? Let us know in the Element 14 community. There's also the place where you can engage with us from Element 14 Presents and a lot of other makers and engineers around the world. And now I've got to go. There's another project waiting for me.